we are doing this delay minimization also, and we particularly considered that matrix transposition problem, that there is a 3 by 3 matrix given to you. Okay, 3 by 3 matrix given to you like this. A, B, C, A, B, you see this 3 by 3 matrix given to you, you have to transpose it, and this is what we came up with the other day, that initially if you just have a reader and a writer, reader reads in 0s cycle, writes in 0s cycle, but then after a while you find that for instance to transpose D to this position, you see reader comes here at cycle number 3, but has to write in cycle number 1, so that was a causality problem. We introduced a latency of 4, we found out the time difference, so there is minus 4 to make it 0, the minimum latency that was needed was 4, so that is it starts at 0s cycle, 08, first, second, third, and then the 4th cycle when it goes here, that time this writing process starts. As a result, the causality problem is avoided, but then you need to store many variables for a longer period because of the latency factor. Okay, as a result, because you are adding 4 cycle to all of these times, as a result you got 12 here, 8 becomes 12, so on and so forth. Okay, 5 becomes 9, 2 becomes 6, all 7 becomes 11, all they have got, I mean, this 4 got added, and these are the life periods. A was to be kept alive for 0 to 4. The 0th cycle is produced, it is to be stored for cycle 1, cycle 2, cycle 3, cycle 4. Then I mean cycle 4 it is out, no need to store further. So these are the life periods, and based on this we do the lifetime analysis chart. Okay, because we know it's generated in cycle number 0, then it needs to be stored in 1, 2, 3, 4, in 4, cycle 4 it gets consumed. So for others we form a lifetime chart, and then it's repetitive, it's an iterative process. I mean, this is 3 by 3 matrix with 9 elements. So after 9 cycles, after you are finished through with this cycle number 0 to cycle number 8, another matrix will be given to you. So because of repetitive in the lifetime analysis chart, there is some overlap. So considering all the overlap and everything, we found that minimum number of registers required is 4. That is the figure we arrived at last time. That even considering this overlap factor between successive periods, successive iterations, we found that the minimum number of registers required is 4. Okay, because at every cycle 4 or less than 4 variables need to be stored. So 4 we are taking because that is the maximum factor. Okay. Then the question came as to how to allocate them optimally, and then we gave one algorithm that forward backward register data allocation. I just start from there again. Based on this, I rewrite we go up to cycle 12 because this 12 factor. So this is one variable which I is one variable which was generated in cycle 8, but has to be stored up till cycle 12. So that is why I have to consider line number up to 12. Okay. But remember, we go up to cycle 12 for first iteration, but second iteration itself starts at cycle number 9, 0 to 8 for cycle. So there will be some overlap. Okay. But this allocation is such that you never reach a situation where one register is being approached by more than one variables for storage. Okay, no conflict, and that is mainly because we have found out the minimum number of registers required for the entire iteration period. Considering our overlap and all, that was 4. That means if you have 4, there should not be any problem. Somebody or other should be available. Okay. When I put a column for input, basically if I say A, then A is generated in cycle 0, no need to store. And there are 4 registers which are required, they were in cascade R1, R2, because data will move from R1 to R2, R2 to R3, R3 to R4, and can come back to any of the backward registers through some switch at appropriate time, and again go forward, forward, backward, forward, backward. But as it goes in the cycle, everybody has a place to be stored. and then once it's consumed, it gets out of this movement. It's no longer required to be stored, and that position will be given to somebody else. Okay, but nothing is dynamic, nothing is static. Of course, if these things are static, then you cannot, because data is moving from cycle to cycle. No? So to move it from register to register. Okay, that is what this algorithm is. It so happen in this allocation, if you consider this, you see in 0th cycle only one variable is generated, next cycle 1 is generated, next cycle B is generated, next cycle C is generated. So, it is a relatively simple problem where you do not have more than one variable being generated in the same cycle. Obviously, because reader is either reading it and then reading it, then reading it, then reading it. It is not reading 2 elements or more than 2 elements in the same cycle. But you can in general have some situations where more than one variables are generated. Okay, so when you have input maybe a comma a prime, okay, 2 can be generated. In that case, how to do allocation? In that case, the rule is find out between a and a prime which has the longer lifetime. Whoever is the longer time, give it the initial register. The other one can come later. Okay, whichever has the longer lifetime, give it the an initial register. Like suppose it is a and a prime has suppose 2 cycles and a has 4 cycles. Then you start with a first, then a prime, not the other way. Start with the variable which has a longer lifetime in terms of storage. Okay. Say R1 is first register, R2 second, R3, R4, like that. Give the earlier register to that variable which has a longer lifetime. If more than one variable turn up. Okay. In this case, it doesn't, but I am telling you the general case. So A is just inputted in this register. Please understand, A is inputted, is an input only in cycle 1. Maybe by a narrow pulse, A goes into this register and remains stored. Okay. So cycle number 1, A is stored here. In cycle number 2, because you see that was the lifetime, right? 0. Cycle number 1, 2, 3, 4. So it just ripples through the registers 1, 2, 3, 4. Once you reach 4, no longer needed. So 1, next cycle it goes here, next cycle goes here, next cycle goes here, and I no longer need it. So I put a circle around it. Means because once it reaches the output of it is stored, means what? The data has entered R4 by a narrow pulse. It has surfaced at the output and is being held there, but I no longer need it afterwards. So in this cycle it is finished. So I say output is A in this cycle. Okay. Next you read B. Next is B 1 to 7. So cycle number 1 is inputted, and it needs to be stored here from cycle number 2 onwards. Well, it goes up to this 4, but I have to go up to 7. Okay, it has just gone up to cycle number 5. Sorry, cycle number 5. I still need to store it for 6 and 7. Then only it becomes dead. But I have already reached this end. That means I need to move it backward, where there is no register in the forward direction. I hold it there. I know that there is one case which is hanging. I need to, but definitely I will have some space for it in the next line. It is because of that fundamental thing that I have found by the lifetime analysis thing. I have found out the minimum number of registers required, and that many registers I have deployed. So in no cycle I will have some shortage of register. Somebody or other will be available. Okay. So I hold it here. Then next cycle C. For C it is 2 to 10 or very long. So, in cycle 2 generated and goes like this. Again I have met with a dead end, there is no other register, but I hold it there. Then is D is 3 to 5, it is not very long. Oh, sorry. Huh? Yeah, I am very sorry. How to take care of this? This D I need to just cut. I reserve it, but I have already made a mark here, isn't it? This is D, so output is D. Okay. So, you see B was generated here. Okay, B was generated. At least I have got one space for B, but there could be more spaces. So, let me first go up to this, because if the situation again comes that okay, there are more than one spaces where to send B, then again you see, I mean the logic is that you give it to the earlier register. Okay. Those are kind of rule of thumbs. I do not think that will change the algorithm much. Okay. So, next is E, there is a space available here. For E 4 to 8, isn't it? 4 to 8. Fine, it goes straight. There is F 5 to 11. I read only up to 9, and mind you, is this in this line new iteration starts, isn't it? So, for new iteration, this register new iteration starts here. So, whatever was happening here, that will happen here, isn't it? Whatever was happening, that will happen here. So, these register I have to actually I will just cross them, so that you do not start using them for data of previous iteration, because they need to be used for the next iteration. I am coming to that, but I have already now filled up this gone, only this is vacant. So, happily I can send that back here. And then it goes here B. B was originally what? 1 to 7, fine. So, I have reached 7. Next here is G. G 6 to 6, generated and consumed, no need to store. G was causing the maximum trouble, you see, it has -4. Because of this guy only I added the latency. So, it so happens in that new system, the moment it is read, it is written in the same cycle. This is the writing is going with a delay of 4. So, when you read here, read 0, 1, 2, 3, 4, 5, 6, the 6th cycle you read here, that time the writer reaches only this place, but I want this to be written here. So, fine, I read it and write, not to store it anywhere, isn't it? So, that means it is generated and consumed in the same cycle. So, I just put this G, isn't it? So, you see 4 registers used up here. And then remaining 2 H was 7 to 9, and I was 8 to 12. Okay. Before I come back to this backward allocation, you see one thing, 0 to 8 one iteration, then cycle 9 again I input new A, say maybe A prime, isn't it, and then again B prime, C prime, D prime. I am not drawing anything below this, I was interested only in one iteration. Since cycle number 12 I had to go up to cycle number 12, I had to draw this line, so some overlap I had to accept. So these registers, like A prime will go like this. So these registers are not to be used for the current iteration. Okay, they are occupied. I am just crossing them out just to indicate that when you do backward allocation, don't use these registers, because A prime will move like this, the way it was moving here. B was moving like this, so B prime also will move like this, and C was moving, so just, so these registers are for the subsequent iteration, so not to be used. That is why I am hashing them, so that I mean when you do backward allocation, I don't by mistake use up some of these registers, because they are actually, even if the fact that I am considering only one iteration for this thing, they are actually to be used for the next iteration. Okay, so they cannot be touched. Now let us complete the unfinished string. B done, only C has a problem. C in the next line, it comes here. Okay. And C's journey was from 2 to 10, and then it goes to 8, 9, 10. Okay. F was hanging, but F 5 to 11, this is obvious. Okay. So now I know how to allocate. This is a table. Now I will draw the hardware based on this. Based on this table, I will draw the hardware. I know which cycle, which data is to be stored in which register, and then in which cycle it should be acquired, move back and all that. Those things I know. Okay. How many registers are needed? R1, R2, R3, R4, 4, and they are to be used in a cascade. So use 4 registers. Four registers. Here it is in, see one thing, except for this G fellow, whatever you are inputting, that is going down this way, isn't it? Maybe it is consumed here, that is a different matter. It is following this R1 to R2 at least, that kind of movement. It is going from input, then entering R1, R2, at least up to R2 or beyond. Again this input, R1, then R2, maybe beyond, that is a different matter. So, input is propagating at least up to R2. Only here there is a problem. Here what is happening? Input is not going to the register at all, it is going directly to the output. And as a result, in the next cycle, that is what is R1 holding that time? R1 is holding, like here, A was generated in the input. So, in cycle number 1 with the narrow pulse thing, A entered R1 and was held up here, stored here. In cycle number purely in R1, but this time it is not happening. G is generated in cycle A, cycle 6 and consumed, okay. And in the next cycle, this data came from C. That means C actually is to be inputted to register R1 in this cycle only. So that in the following cycle by a narrow pulse or whatever, there is a trigger, that data enters R1 and remains stored there, right. You are following me? This simple digital hardware logic. Cycle 6 I am talking of. In cycle 6, for the input there is no need to store things in the registers. But this R4 output, this is R4 output is C. I should directly connect C that time to the input of R1 in cycle 6. Mind you, it is not entering R1 in cycle 6, it is giving only at the input. Only the next cycle by a very narrow pulse, this data enters R1 and remains in R1, stored in R1. Are you following me? So, that means in cycle 6, input to R1 should not come from the data that is read, but it should come from R4 outputs. There should be a switch. Afterwards again, whatever you read, it goes into R1. Okay. That means here how they draw the switch, okay, like this. There is a switch. This fellow always connects to this fellow except for cycle number 6. Cycle number 6, general cycle number 6 I will write 9L plus 6, iteration period is 9, L equal to 0, 0th iteration, L equal to 1, first iteration, like that. So, 9L plus 6, Lth iteration I am talking of, 9L plus 6. During that time this guy will be connecting and it will come directly from here. Are you following me? Look at this 9L plus 6. Na? Only at this time this guy connects, otherwise always here. So, at least data A, B, C, D, E, F, forget G and again H, I, they move in to R1, then I will connect, make this connection, go to R2, R3. Only in 9L plus 6, this input will go to some output point directly, that I will show, but R1 input will be coming from R4 input. Whatever is generated at R4, you present it directly to R1 to be stored there in the next cycle when a narrow pulse comes. Okay, it is generated here in 9L plus 6. So, at the same time make it available to the input of this. Yeah, 9L plus 6, 9L plus 6. At that time it is generated, the variable C. Also at that time only you connect it here. So, in 9L plus 7 this guy will enter in here, 9L plus 8 may enter here, like that. Okay. There is one out. That means this out will take in directly only here, only at 9L plus 6. This switch will connect to this. There is G read and G presented at output in the same cycle. So, at 9L plus 6, this gets connected to this side and this gets connected to this output side. That is pretty simple. Okay. Then comes this. You see, in all of them, if whenever there is somebody in R1, it always goes to R2. You won't find any exception. R1 to R2 movement is common to all lines. That means there is a line directly. Here there is no switch needed. You see, R1 to R2, R1 to R2, R1 to R2, R1 to. After this, it gets consumed. It is different matter. That this fellow and this fellow, they no longer move to R3 and therefore to R4. Once this guy and this guy reach R2, finished. So that time, this guy and this guy need to be switched back to the output side. Okay. That means R2 output, except for these two lines, is always going into R3. Only here and here, it is not going to R3, it is directly going to output. Okay. That time what is comes as R3, like here, what will come is the input of R3, whatever is this guy. R4, like I am making the allocation na, in this line. What is the R3 input? R2 output is this, but instead of giving it to R3 input, I give it to the output. So during this cycle, cycle number 5, what should be presented to the input of R3 to be stored there in the next cycle? This guy B, that is the allocation. So R4 output should get connected to R3 input at this cycle only. Okay. So that moves, instead of D, that moves here. Okay. So at R2 there is a switch thing again. R2 output goes to output terminal in cycle number 5 and cycle number 9, and cycle number 9 is equivalent to cycle number 0, modulo 9. So that means cycle number 0 and cycle number 5, R2 does not connect to R3 input, but it connects to the out. So here you write 9L plus 0, because 9L plus 9 is equivalent to 9L plus 0, comma 5. And during this time, when it gets connected here, that time the switch should move here. On this occasion also, how is the allocation? Like instead of D moving to R3, which moves to R3? B moves to R3. B moves to R3. That means in place of D, I should bring back B as at the input of R3. So then the next cycle, R3 absorbs that, as I told you already. As soon as B is generated, I present it to the input of R3. Like D was generated and presented at, otherwise would have been presented at the input of R3. Instead of D, I send in this guy. So when again narrow pulse comes, it enters R3 and gets stored. Similarly here also, F was allocated to this guy. That means instead of giving H to the input of R3, I give F to the input of R3. So that in the next cycle, in this cycle, when a narrow pulse comes, F gets stored in R3. Okay. That means in these two cycles, here and here, that is 9L plus 5, 9L plus 0, R3 takes input from the output of R4. Isn't it? This, please don't get confused that okay, I am showing the arrow here, but I am considering this cycle. I am not saying that it is 9L plus 6, it should be 9L plus 5. This cycle, this indicates the cycle in which it is stored. This data will be input to that register in the previous cycle. Like B was generated in cycle number 5, at the output of R4, that time only a connection should be made to the input of R3. It's a 5. So that in the next cycle, that is cycle number 6, by a narrow pulse, it gets to, I mean, it enters this register. Okay. So, quite clearly H and D, one is let 9L plus 5 and 9L plus 0, that time H and D directly connect to output, R2 output goes to out, and R3 in comes from R4. R3 input comes from this and this R4. So, that means there will be a switch here. When this goes to this side, during these two indices only, 9L plus 0 or 5, R3 takes feedback from here. And once again you see from R3 to R4 there is no problem. Whenever any data is in R3, it always goes to R4. So, there is a direct connection again, no switch in this path. From R4 output, here it goes to out, here it goes to out, here it goes to out, 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 out. So, what are the points? 9L plus 4, 7, 8, 1, because this is 0, 1, 2, 3. One, 2, 3, and then 4, 7, 8, isn't it? 4, 7, 8. That's all. Okay, you will go on giving the in this data as per the cycle numbers. And the transpose matrix will come out. You see A, D, G, you are writing in this sequence A, D, you are writing this way, na? First row A, D, G, then B, E, H, then C, A, Phi, write a rates like this, and there is a latency, 4 cycle. You read it 0th cycle, but you started writing at cycle number 4. Okay. If you take this output sequentially means what? We have given you the pattern of our writing the data row wise. First row, first column, first row, second column, first row, third column, then first, second row, first, like that. And if you write a matrix like that, you get the transpose. You see ADG, BEH, and then CFI. But you are giving the data in this manner to the input. So, there is no delay in the system. I mean, just 4 delays. There is no extra delay in the system. Okay, there is minimum delay. There is delay, but there is a minimum delay. We cannot make it less because our lifetime analysis said that. I suggest that in the book, they have given 1 or 2 examples, especially that filter. You remember that we were doing folding on an IIR filter, which was almost like a direct from 2 structure, but for some redistribution of delays, which was a schedule also, and for that it was not showing any negative edge. Okay, but actually that was obtained by retiming the original direct from 1 structure. On that, finally I give you the folded hardware in terms of just one pipeline data, pipeline multiplier, and delays and switches. So, there delays were there, D, 2D, 2D, and all those kind of delays were there. On that circuit, if you have to do further delay minimization, delay optimization, then what happens? Then again you have to find out and have to carry out an appropriate lifetime analysis and all that. Then this forward backward data allocation business, and then the structure that is elaborately given in this book. I will not get into that. I suggest you to read that, but I might get that kind of problems. Okay, you read that. It is given just subsequent to this. That problem is given. Read that part. That's not difficult. So, finally, you get a structure where both hardware units are also folded and delays also are folded. But delay minimization means you are sharing the delay. Instead of using so many delays, you are using minimum delay and having them shared by switches, isn't it? So, that is I call it delay folding. Folding delay, folding hardware units. All together, the final structure that is given. So, that is about folding. I move to the next topic. It's a very interesting topic, that is systolic arrays. You have a background of matrices, null space, range space, and all that. Do you have? All of you have some idea about null space of a matrix? No. Anyway, I will see. Systolic arrays, I mean, starting point of systolic arrays is what we mentioned in the very beginning of this course. There is one kind of representation which was SFG, that was no good. Then there was DFG, which has been used and which will be used in this course most of the time, but there is another representation which is DG, dependence graph. And I told you that time that dependence graph is something for which there is no systematic way of drawing the dependence graph. It needs your experience and intelligence and all that. And DG is particularly useful. DG, what is the beauty of DG? DG, you remember the DG? Let us draw a DG again, in case you have remember. You consider that FIR filtering problem. B0 xn okay, you define a processor like this. Processor needs to be defined. If you call it A prime, X prime, the three input Y, three inputs are A, X, Y, three outputs in this direction are A prime, X prime, Y prime. Then the purpose is X prime remains same as X, A prime remains same as A, Y prime does that MAC operation A X plus Y. That is the nomenclature or definition of my processor. Okay. This where directions are very important. These are the edges. This is the node which is denoted by a dot, and these are edges. And using that, we had drawn the DG. In a DG, if you see this plane, wherever I am drawing, all the points, all the coordinate points are to be filled in, will be there. It is not that some particular coordinate point is left out and all that. So, all these are dots. And that has to be, because I am considering output at each index. Actually, I do not need these two lines, sorry. These two lines I do not need, because this is just B0 this is implicitly the time axis. So, you give x maybe 1 here, you start with n equal to 1 say, x 2 here, arrows are very important. We had done it in the class, so they are in your notes. So on and so forth. If you are in clumsy, so I am not drawing it. You understand the operation easily? Y1, we are assuming 0 initial condition. So, Y1 is just B0 x1. So, B0 B0 x1 plus 0. And what is y2? Y2 will be B0 x2. So, B0 x2 and whatever comes from here, before that B1 xn minus 1. So, B1 x1, x1 also moves up, B1 x1 plus 0, that output comes here. With that B0 x2, this product gets added and comes here. At B0 propagates, B1 propagates, B2 propagates, like that. Okay. Are you following this? This was done in the class, or you have forgotten? DG. You have forgotten or you remember? Remember, right? Fine. Okay. Because I don't understand, na? I mean, this is okay. DG is the starting point. What is there in DG? DG is very systematic, very regular. Whatever pattern you have, that repeats itself. Starting from DG, and this is just a two-dimensional DG. I also mentioned one thing, that even though it is not, there is no systematic procedure to do a DG, but one thing is there. What is the dimension of the DG? You know, it depends on the number of iterations. Like here, if you write an algorithm, I mean not number of iteration indices. Like if you write an algorithm, there will be first one index over n, therefore suppose n equal to 1 up to say 500, do, there is a loop, and within the loop again you are finding out the output. There is another index I, say bi, b0, b1, b2. So there is another loop over I equal to 0, 1, 2. You understand? You can write the algorithm easily this way, na? Say for n equal to 1 to say 500, you want to see the output from 1 to 500. Okay, and then you give y as 0. Okay, and then again for say I equal to 0 to 2, y equal to y plus bi n minus I, isn't it? Like this. I am not completing it. So, y changes, you start with the y equal to 0 and then y gets modified. All x I am assuming to be given to be 0 for n less than 0 or n less than equal to 0. That is not written in the algorithm. Okay. And then y equal to okay, so, but how many loops? Forget about or how many iteration indices? 2, isn't it? Here for this problem 2 iterations, and the DG also will be 2-dimensional, because whatever data in the form of x or data in the form of coefficients, okay, whatever I am giving, I have to give over one index over its range, and also have to give over another index over its range, so on and so forth. In the entire algorithm, there are suppose L number of indices, okay, I, j, k, like that, total L number of indices. So, all the system variables, algorithm variables and all, so they are actually to be defined, they are to be given over each index over its appropriate range. Range is not the important, range how many points I consider up to 500 or 5 lakh, that is not important, but dimension, each index corresponds to one dimension. Like here the I index was corresponding to y axis, n index was corresponding here. You consider other DGs, I will consider some other DGs also, there will see, there will become 3-dimensional, it is 2-dimensional, it will become 3-dimensional. So, this is important for DG. Now, I am coming to systolic arrays. In early 80s, this thing came up, that they found out, I mean they found that, okay, I mean many, they have got such beautiful structure inside, because it is repetitive in time and all that. So, it is beautiful structure inside, that the DG can be used after some manipulation and all that to implement that algorithm in a very regular structure, using borrowing the regularity of DG. DG is very regular, because whatever pattern you have, you see everywhere the same pattern repeats. Basically, this procedure, okay, this repeats using the regularity of the whole algorithm can be, I mean, implemented in an array which is a very regular array, could be 1-dimensional only, could be 2-dimensional or 3-dimensional. You cannot make it 4-dimensional in real life. Okay, but array, very regular array. Regularity is very important for VLSI because I mean, whatever mask or you have for one small segment, that gets repeated, okay, because of the regularity. Further, you can introduce delays by retiming, appropriate retiming in the edges, okay, in that array, so that critical path becomes less. In fact, all edges ideally should have delay, so that the time constraint or critical path will be given by the maximum node computation time. Then there should not be any long connection. It's not that one node connects to some further other node by an odd line and all that, those can be avoided. Like this DG, there is no long connection here. Every node is connected only to its neighbors, and that was very, very nice for VLSI implementations. No long connection, so it's highly pipelined. The critical path computation time can be brought down to just one node computation time and very regular. And those kind of structures were called systolic arrays. Systolic array because it is pipeline structure. So, suppose you are injecting the input like this B0, B1, B2 or this data, inject the input to this array somewhere, then that data being processed by the first stage of nodes, that goes to the second stage after the one cycle and then after another cycle, like that, it's as though it's body and there is a heart that is pumping blood in the body, and whatever blood quantum, suppose blood is coming out in a quantized manner, whatever quantum of blood comes out in a current cycle, that does not reach your fingertips in the same cycle. It goes through the body through several cycles and reaches there. Again, whatever with the reverse, in the reverse direction, that also comes back to the heart. Suppose it is generated by this part of the body or this part of the, it also comes back, not in the same cycle it was generated, it comes back in some other cycle, but everything is in a very synchronous manner. Okay, so people somehow viewed that it has that kind of pattern. So this name systolic array was given in relation to this, I mean, heart's pumping of blood and also this reverse flow of blood and all that. That was the reason for giving this name systolic array, as though this data and all are pumped through the array. Okay. Now, sometimes you can design these arrays just by using your intelligence and all that, but you need a formal approach to these arrays. Formal approach is this, that maybe you can, here it is a 2D DG, starting point is a DG, you have to draw a DG, there is no escape from it, you have to draw a DG, and DG could in general be an n dimensional DG, capital N dimensional, which cannot be drawn here, and I have to map the DG then, n dimension, if n is 4 or 5 or 6, I cannot implement the DG. Even here there is another problem, that time axis was growing, so if I have to implement it, I have to make an infinitely long DG, IC, which I cannot, there is a separate issue. That can be taken care of later, but at least dimension wise, if it is more than 3 dimension, then I cannot realize it in real life. Real life IC can be 3 dimension, or within IC there can be a slice of 2 dimension or just an array of 1 dimension. So that means you start with a DG, if its dimension is greater than 3, say capital N number of dimension, you then have to have some mapping of that original DG, n dimensional DG, to a DG which has dimension at most equal to 3 or 2 or 1. So capital N dimension 2, say 3 or 2 or 1 dimension mapping, but you should map such a way that regularity of the original DG does not get disturbed. Okay, that is very important. Regularity of the original DG does not get disturbed. How to do that? Okay. Now, the original DG, you consider an n dimensional space. Consider n dimensional DG. That means, like a 2 dimension, there is an n dimensional space, okay, n iteration indices and all, so n dimensional DG. Each point there, like each point here, each point there has got a set of coordinates, like this was having coordinate 1, 1, this is 1, 2, 1, 2, 3, 1, 1, 2, 2, 2, each point in that n dimensional space, and no point is left behind. It is not that I will take some points, mind you, this is important. It is not in a DG, in the space, certain points are not to be used and certain points to be used, not like that. Every integer points, every coordinate point with integer coordinates needs to be used up. That will be used up because I am not leaving any index. It is not that from 0 I go to 2 or then 6. I am considering the index space thoroughly. Okay, I am not leaving it. So that is why all points need to be, all points will be used up, but that is very important. So, in a DG you consider a particular point, a point is a vector I, I call it IN, underline means vector. It will have some coordinates here, say I1, I2, say IN, all integers, one particular point. I will be mapping one DG to a lower dimensional DG, means each point is to be mapped to an equivalent some point in the lower dimensional DG. Okay. Now, in n dimension 2, n could be 10, I have to bring it down to 3 or 2 or 1. That is a general problem, it is more difficult. For this course, as this book says, I will be only considering transformation from n dimension to just n minus 1 dimension. So, given a 4 dimensional DG, I will transform it to 3 or 3 to 2 or 2 to 1, and that way if you cascade, you can go from 5 to 4 and 4 to 3 that way, though it is not done that way, it can be done directly. But at least for your satisfaction, if you are given the problem of converting a 5 dimensional DG into 3 or 2, you can repeat this stage, though there are better ways of doing it. So, I will be mapping an n dimensional DG to n minus 1 dimension for our course, n minus 1 dimensional DG. Map to there, that is IN will be mapped to a particular point j n minus 1. This belongs to the lower dimensional DG, this is a higher dimensional DG. Here the coordinates could be j1, j2 dot 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 j n minus 1. Okay. One very important thing you see, if you look at this any DG, say consider this DG. What defines a DG? If I do not give you the, suppose I do not give a diagram. Okay. Entire DG is defined by these basic edges. One edge, this edge, each edge is a vector. In this 2D plot or in dimensional plot, each edge is a vector. Okay. There is one edge in this direction. There are 3 basic edges you see. In this DG there are 3 basic edges, isn't it? One in this direction, another in this direction, another in this direction. Okay. What are these 3 edge vectors? These 3 edge vectors, if there is an origin, one edge vector is this, which is nothing but 1, 0, vector 1, 0, or you can write vertically also 1, 0, okay, because of lack of put a transpose 1, 0, isn't it? If you go on adding this vector to this nodes, from this node you arrive here, to that node you add another vector, you arrive at this, from to that you arrive at that edge vector, you arrive at this, so on and so forth. There is another vector in this direction. Time is short, so I am just here. Okay. If you go on adding this vector to various nodes, you go from here to here, here to here, and there is another one in this direction, start at the origin, and that is what? 1 minus 1 transpose. If I give you these 3 edges, you can construct this DG easily without knowing anything. You just fill up the space with dots, no point has to be left behind, okay, no point has to be left unused, all 1, 1, 1, 2, 1, 3, like all points. And then what kind of edge connection? Simply use this edge vector to connect the nodes. That means that DG is completely defined by the edges, edge vectors. No need to draw it like this. You can define an DG purely by the edge vectors. So, while transforming, I will not be doing, while transforming one DG to another DG, I will not be foolishly approaching each point and defining the transformation. I will be looking only the edges, few edge vectors of the original DG. I will give you transformation rule for them. Anyway, I'll continue from here in the next class. It's a very interesting topic, mathematically and everywhere. Okay. Thank you very much.